Hello. Hello.
Hey.
Can you hear me?
Yes, I can.
I cannot hear you. Let me see what is going on. Why I cannot hear you? Just a moment. Okay. Okay, now let us try again. Can you hear me now?
Yes, I can.
Very good. Now it seems that we don't have today here guys from TalTech present here, so probably they are going to look videos later on. So, well, I am happy as long as there is at least, okay, now one is coming, because, well, I am fine recording things, but, you know, if no one is present, then there are no questions, and I might go too fast and skip things, and so it's better still to have at least two of you present, because, well, yeah. But no, and yeah, here they are. There are now two more coming here, so I have three guys in the room, and so we can start. Okay, we have this screen here, and now before we start, I take the copy paste from last time. We have I brought down formula, which will be going to use this time. So just a moment. Over here, yeah, this one here. Let me copy this. Copy this one to our new slides. Okay. And now, before we start still with that, regarding the homework, how did it go? How everything is going fine? You homework now?
We just finished the simulation for the sine flow.
Okay.
We didn't plot the result, but I guess that it should be fine.
Okay. Let me see. Are you, if you don't have it, that's fine too. But if you have it, it would be nice. I'm always curious to see how.
Like the code was this one, but the result.
All right. Okay, so you can just send me by email, and then once I got some pictures to show, then we'll all having a look on what you have, because I think that's the fun part, having a look on the figures and pictures. Anyone else something to say about homeworks?
Did you get mine?
Yeah. What right? One more sentence. That was fine. The average of the distance to the power of alpha, how did it go? Did you manage to do something, or you still thinking to work on it later?
Later.
Later. Arthur, what about you?
Sorry, I missed, I think, the last two sentences.
I'm asking, how did your homework go? So one is the distance to the power of alpha, finding average.
Oh yeah, that one I figured out. So that one went all right.
Mhm.
And yeah.
And then the other one was the how the cooling plate was yeah, hot plate with water. How did that go?
I think that one also went all right. Let's take a look.
Okay, you don't just ask if everything is fine, because once you're done, you can just send me scans or something. So no need to show right now. Just take your time and send it later. And the same applies to everyone. So once you feel you have finished, please send me like right already. And now going to continue. What I showed you last time was a figure with the what happens on the surface of water, and maybe it's useful to open this as well once again. Just a moment. Let's see if I have PDF still open. Oh no, this was a previous lecture. I have too many things open, so I think I have also okay. Yeah, sorry, I need to a little bit this. Yeah, I wanted to show the same picture what I showed you last time, but unfortunately, it seems I did not copy it to my screen here. The lecture from last time. Yeah, sorry about that. It's taking a little bit time. I think this one here. Now I found. Okay. Let me share the proper screen. And here you go. So if you have partially compressible flow, then things which float on the surface will start gathering into wedges. And last time I explained to you that we can introduce the concept of compressibility, which describes then to which extent it is compressible. And to that end, you need to do what is called Helmholtz decomposition, in which case you separate field into potential and solenoidal components. Let me take a screenshot here and then copy this to the main slides, and okay, here. And let us now go back to the previous screen when I had the Helmholtz decomposition written previously. It was, I guess, here, yes. So you express velocity as the sum of solenoidal component, which is curl of vector potential. And in 2D case, in two-dimensional case, you can the vector potential reduces down to stream function, because vector is always parallel to z-axis. So that the Vs, this equation here, is what I'm speaking about. I have also the laser pointer here. So this equation here, what I'm speaking about. And then we can quantify the importance of the first and second term as compressibility, which is defined as a relative weight of the Frobenius norms of these two components. And now it appears that, well, in the case of water flow, on top of a liquid, the compressibility is fairly close to 1/2, 0.5. It's like experimental fact. There is no easy way to prove it mathematically, but the experimental fact is it's very close to 0.5 compressibility at the surface of liquid. Let me copy this again also now to your screen. Now, by that compressibility, what you still need to keep in mind is that not every compressibility is what we actually what will start bringing particles together. So last time I explained to you that the reason why particles start gathering into patches is that average over space is not equal to average over time. So there is no ergodicity in this case, meaning that yeah, and the reason is that the particles are pushed out from expanding regions. So if you have diverging region, particles which flow to the surface are pushed out and they come in the other way around. They are converging and gathering into patches, and so they stay for a long time in converging regions and go away from diverging regions. And so if you average the divergence on the place of a bunch of particles, it becomes negative. They start contracting. And then I also explained to you that in that case, you need to describe things in terms of Lyapunov exponents, which we did need only the largest Lyapunov exponent beforehand. Well, the reason was that we were considering two-dimensional flows. Now let me go here and start explaining here. So we considered only two-dimensional flows. So if we have like ellipse or a 3D ellipsoid. So circle evolves into ellipsoid. If you mark on a fluid a circle, it evolves into ellipsoid. And then we say that if this here was unity, and then this side here is e to the power of lambda 1 t, asymptotical in time. If you wait for a long time, this length, the longest side starts growing to e to the lambda 1 t, and the shorter one to e to the lambda 2 t. And now, because in 2D, the volume is conserved. V is e lambda 1 t times e lambda 2 t. So, but this equals, due to the property of exponent, e lambda 1 plus lambda 2 times t. But we know that this is constant because it's incompressible, so this must be constant. So we conclude that this guy over here is 0. Lambda 1 plus lambda 2 is 0. If we have incompressible, is incompressible. On the other hand, now we don't have incompressibility. So if compressible, then there is no this constraint. Otherwise, and now we know that it starts contracting. So otherwise, lambda1 plus lambda2 is less than 0, because in average, the surface area starts converging. Now in 3D, in the same way, you would have 3 exponents, because now as is in 2D is ellipse, in 3D it's ellipsoid, and the ellipsoid has 3 major semi-axes. 3D V in the same way is E lambda 1 plus lambda 2 plus lambda 3 times T equals constant. So lambda 1 plus lambda 2 plus lambda 3 equal to 0. Now, now comes actually important difference between real. Yes, please.
We consider the matrix transformation between one volume and the other. Then we know that the volume is like the ratio of the volumes is the product of the eigenvalues of the transformation matrix.
Yes.
And that one that is 0 is the trace.
Yes.
Right.
Yeah.
Then, like, if we put together the two information, like, what does it tell us about the transformation itself? Like the sum is 0 and the product is 1. There must be some, I don't know.
Yeah, if you want to do some math here, that can be also done. If transformation of circle into ellipse is, let me do some math here on next page then. If we write down now equation, starting equation, so we have something like that from one particle to other particle distance vector. So we have dr i's component of vector. This is vector pointing from one particle to the other, divided by now coordinate j's coordinate. No, wait. dr over I over dt. Yeah, because I'm not quite prepared, so it might not go very smoothly, but let us see. Dri over dt is going to be equal. And now goes the strain, so-called strain tensor. So we have velocity field v as a function of coordinates. And now, what we need to have here is d vi over dx j multiplied by j's component of the vector. Is that right? Should be. So this is what we need to have is a relative speed of the second particle related to the first one. So here is our first particle. Here is our second particle. Here is a vector pointing from here to here. So this vector is vector R. And now we write i's component, and because we calculate a relative speed of that, we find by Taylor expansion. So we need to have i's component of this velocity vector, and by Taylor expansion, we expand it by j's component and sum over repeating indices. And then this thing here is called strain tensor. And then formally, this you can write it in tensor form, like vector R is time derivative of it is a tensor, strain tensor the gradient of v. Let me write gradient of v as gradient of v. Gradient of v is tensor, right? And then multiply dot product with vector r. The same thing written in tensor form. Is it okay, everyone? And formally, you can solve this in the form. You can write the solution here that r equals r naught e to the power of, and now goes tensor, gradient of v as tensor, and dt and integral. These are like formal solution to this thing here. So as long as you know how to take exponents of a tensor, then that's it. And now, if you want to have a metric tensor, then you need to take length of r, and then you take r multiplied by r transposed, and this goes to if we say that this guy here is set the matrix A, and then you have r naught multiplied by A and matrix A transposed and R not transposed. I think this happens when you calculate the modulus of R squared. Something like that. Linear algebra, basically. And so this, which means that actually metric tensor, which defines the length of it, is A times A transpose, which is a symmetric tensor. And now what I'm looking for are the eigenvalues of this metric tensor. This metric tensor, because it is symmetric and positive definite, we know that the result is going to positive always. Symmetric tensor, positive definite. So it means that the eigenvectors of that thing are perpendicular to each other. And yes, and the volume is the volume is the product, and then yeah, if you compare now these two things, if you take this integral over there, exponent of a tensor which is matrix A, then you can relate the trace with the product over here. So basically, a product of the volume here is a product of the eigenvalues of this. In if you make now represent this tensor here in a diagonal form, the volume is going to be the product of the eigenvectors. On the other hand, if you speak about the term of the exponent here, then it comes down to the sum of the eigenvector, the trace of the matrix. Did I answer your question, more or less? So it's just a fairly mathematical thing, actually, and linear algebra, what you need to work with. But yeah, this was just like how it mathematically works out. But we are trying to avoid as much math as possible. So yes, so we have now in 3D, this comes down to the trace of the matrix in the exponent, sum of the Lyapunov exponents. So Lyapunov exponents are defined. Just let us finish with mathematically what we have. We have this guy over here. So this, if we have symmetric positive definite tensor, this can be represented in a diagonal form. And then this guy over here becomes equal to, let me change color. And this tensor here becomes equal to takes form in diagonal form, right as so e to the power of 2 lambda 1 t 0 0 0 e 2 lambda 2 t 0 0 0 e 2 lambda 3 t. This is the diagonal form of that matrix tensor over there. And then the volume is a product of those, and so you'll see that the volume is going to be this is squared length. So in order to obtain length to the first power, it takes square root, so 2 goes away. Volume is the same thing: e lambda 1 t, e lambda 2 t, e lambda 3 t. Okay. Now, the next thing to notice is that apart from the fact that lambda 1 plus lambda 2 plus lambda 3 is 0, is that, well, it appears that if we have a reversible flow, which means statistically, if you reverse time error, like you look at the flow in positive direction, and then you just start rewinding it like in a video in the reverse direction. So it's statistically forward flow of time and reverse flow of time are identical. And then lambda 1 equals to minus lambda 3. Let me write it down as well.
Don't we have a problem with entropy?
No, not really entropy here, but well, we'll come to that. What happens with real flow, we'll come to that point. But for the time being, if we have, if the flow is reversible statistically, then lambda 1 equals to minus lambda 3. So can I somehow to try to motivate this? So what we can do is that take a flow which deforms a sphere into ellipsoid. And then take here draw another ball here. Now, and now reverse time. If we reverse down, the blue one will go to that one here. Okay. But what happens with the red one, because now it was long that way, it becomes compressed that way. But red ones now becomes that way. Okay. And so as many times as the blue became shorter. So we'll see that it is as much red is as many times became as many times red as many times longer as the blue became fatter. Also, fatter. Let us write fatter. It became very thin, but now if we reverse time, it becomes fat again. So we see that's the same exponent which describes elongation. If you go from a blue circle to a blue circle over here, the same exponent which describes lengthening of a blue describes now in reverse time the other way around. So here, like length here, let me write down here. So this is unity. This unit length over here. Okay, this is unity. Now this here is e to the power of lambda 1t, because this describes how much it longer becomes, the largest exponent. Now, if I go back in time, so this becomes now, if I go back in time, so the new length is e to the power of lambda 1t. And now, in order to make the length again back to unity, we must multiply this to e to the power of minus lambda 1t. So we see that we need all the lengths in that direction need to be multiplied by e to the minus lambda 1t. And now this means that the red one here becomes respectively narrow. Now the red one is in reverse time is this length over here is also e to the power of minus lambda 1t. But now here for the in reverse time, this is a third largest exponent, because it's how narrow now it became. So on the other hand, in reverse time, it is e to the power of lambda 3t. From here, we can conclude that lambda 1 equals to minus lambda 3. More or less clear? That if we have statistically time arrow is isotropic, then we have lambda 1 equals to minus lambda 3. And together with the condition lambda 1 plus lambda 2 plus lambda 3 equal to 0, this means that lambda 2 must be equal to 0. And if we mentioned last time Crichton flows, Crichton flows are like synthetic flows which are delta correlated in time. These are definitely time reversible, because it's very short time. It doesn't matter which way you compress. Stage is always the same way. So Crichton flows are time reversible. So with Crichton flows, you always have lambda 1 equals to lambda 3, minus lambda 3, and lambda 2 equal to 0. But not so in the case of real flows. So in real flows, now I'm a little bit sorry that I don't remember exactly. There is like from experiments again, there is a certain relationship. I think lambda 2 is something like lambda 1. I need to check it. It's just I don't remember the number. Like universal ratio between lambda 1 and lambda 2 from experiments. But it is lambda 2 is definitely not 0. Lambda 2 is negative, so it means that the line becomes both is compressed by both in two directions and stretched in one direction. And yeah, so last time we did speak only about the largest exponents, and the reason is that in 2D we really compress. If we have compressible flow, we really don't need only one exponent. But in 3D or if we have a real flow which is not Greifel flow, not idealized Greifel flow, then we definitely actually we would need to give specify actually two exponents to describe it properly. But in the case of Greifel flow, it's still only one exponent which really describes the state. On the other hand, if we have compressible flows, then we need also exponents. And then depending on the flow, you might have this or that situation. Now, apart from the exponent values, if I go back to the first slide, actually here, not this one here. So the expression what we have for Greifel flows is here. And then we can see also here put into the number index I over here. So let us take from here now the dimensionality space. Let us put it, for instance, d equals to 3. Then in that case, lambda 1 equals certain constant d1. So that d1 is basically a fixed number, fixed constant. And now d is 3. We obtain 9. 3 times 3 is 9. Up 3 multiplied by 3 minus 2 plus 1. And minus compressibility. Minus, now let me write instead of that fancy P, which is written here, let me write C, what I used before, 2. But I'm not going to fit it in this line, I guess. So let me continue on the next line. Minus 2 multiplied by compressibility, and goes into the braces, goes 3 plus 3 minus 1 is 3 minus 1 is 3 minus 2 is 1. 3 minus 2 multiplied by 1. Okay, and braces closed. Now let us rewrite it. D1. So 3 minus 2 plus 1 is 2, 6. 6 minus 2 multiplied by C multiplied by, here we have 2. 3 minus 1, 2 is 1. 1 times 1 is 1. 3 plus 3, 1 is 4. Minus 8C. Everything fine? That's fine. And yeah, we can still rewrite it like 3d1 2 sorry 4 2d1 and 3 minus 4c. So that's more or less how you can work with this lambda sub I. You calculate lambda 1, same way you can calculate lambda 2 and lambda 3 by plugging in I equals to 1, 2, or 3. So here we have I 1, 2, or 3 goes in there if we have d equals 2. Now, let us take now in the case of d equals dimension is 2, which is practically more important case because mostly we have in real life we have incompressible flows on the surface of water, which is two-dimensional. So we have now, let me write for lambda I takes 1 or 2. Let me simplify with d small equals to 2. So we have a d 2 multiplied by 2 minus 2i plus 1 minus 2 compressibility, and goes 2 plus 0, because this small 2 minus 2 is 0. Okay, and brace is closed, and we can rewrite it as now we have here 4 first term 4, second term 4, so we can bring 4 before the braces, 4d1, and then goes oh no, sorry, 2, because here we have 2 minus 2i plus 1. So it goes to 2d1, and then we have 3 minus 2i, and minus 2c. Now let us, for the beginning, let us assume that we have compressibility 0. And if we have compressibility, let me write now. I mean, maybe better we just still rewrite it for lambda 1 and lambda 2. So lambda 1 from here equals now 3 minus 2 is 1. 2d1, 1 minus 2c, and lambda 2 equals, and we have now 3 minus 4, which is minus 1, so it is minus 2d1, and 1 plus 2c, like that. So we have now got expressions for lambda 1 and lambda 2, and we can see that actually here, indeed, if we have compressibility 0, then we have just lambda 1 is 2d1, and lambda 2 is minus 2d1. So as expected, the sum is 0. On the other hand, if we have a compressibility non-zero, then we have lambda 1 plus lambda 2. We can also write 2d1, and then this unit cancels away, and here we have minus 2c, and here we again also minus 2c. So overall, from here we have minus 4c, and from here also coming minus 4c, overall minus 8c, minus 8d1 and c. So if compressibility is 0, volume is conserved, lambda 1 plus lambda 2 is 0, otherwise it's proportional to compressibility. So this is what you can do with the formula which I gave. For again, this is for Greitner flows, for ideal Greitner flows. And what starts being important is actually it appears the ratio of those two exponents. Now, in which way this becomes important. Now, before we go to that topic, we need to mention a little bit about fractality and self-similar structures. Now, please tell me, how much are you familiar with the fractals? Little bit. Now, what about the rest of it?
The idea or computationally? The idea or
well, ideally, yeah,
Yes.
Yeah. So, Arturo, you are also okay with fractals?
I'm familiar with the idea, but nothing in detail.
Okay. So maybe we can consider a little bit the fractal structures, a small recap. So fractal structures well, something which are self-similar, which means that if you zoom in, it is the same as the original. So the most perhaps widespread example is Sierpinski glass. So we take a triangle, start cutting off. And then from the remaining triangles again, you cut off like that. And then so on and so on. So if you want to draw triangles, actually a little bit funny thing to do is if you know few commands of PostScript programming language. So you know that, or if you print things, it goes usually as PostScript. Well, nowadays also as PDF. So PostScript actually, while it's mostly used for printing, for printers, so like printer language, how they interpret images. This is also actually a kind of programming language, which supports recursive commands. And if you go into it, actually, this Sierpinski gasket can be drawn with just a few lines of PostScript file will draw you this shape. And I can later on give you maybe during break. Well, we haven't been making breaks, but anyway, for the next time, I can, for instance, I can give you the sample code for PostScript, how to create for instance, Sierpinski gasket using PostScript language. It's just for fun, nothing else. So, which recursively just generates this thing over there. Now, but more importantly, fractals are characterized usually through fractal dimensionality. And there are different possible ways to define fractal dimensions, but main lesson is that almost all of these are equal to each other. So, like mathematically, most basic one is so-called Hausdorff-Besicovitch dimension, which I don't. Yeah, basically, what you start doing it in the case of Hausdorff-Besicovitch dimension is that you start covering this guy here with, let us say, with circles, and start look how many circles of given size you need to cover this guy over here. And then you define you say that a break into pieces of certain size, and then you say that the total mass of this would be the sum of the pieces. I think I started a little bit wrong way. I just did not plan too much to tell you about the fractal dimensions, and now I'm going a little bit more details as I planned. But yeah, basically you divide this into smaller pieces, and say that each piece has a certain dimension d, and you take this as a dimension of d to the total mass, so to say. Hausdorff-Besicovitch measure is going to be the sum of the pieces d to the power of alpha, and you find such an alpha, and you take limit maximum, you sum over all the pieces, and the size of the largest pieces must go to 0. di goes to 0. The piece, divide all the thing into species of size d, I piece as size d, d sub I, and you consider a process where the maximal size goes to 0, and you find such an alpha that this is finite. So neither 0 to infinity. And then alpha, Hausdorff-Besicovitch dimension. Okay, actually alpha is d. If alpha equals to d gives finite m, then we say that then d is a Hausdorff-Besicovitch dimension. The Hausdorff Hausdorff-Besicovitch dimension. I'm not sure if I did not make any spelling mistakes, but something like that. And DHB, D equals to DHB. And this is a little bit not very convenient definition. So usually use a different ways of doing it. So you can start covering it by circles or something, and say that the number of circles, if so, this goes to as number of circles needed to cover this stuff over here. If this grows as the size, let us say radius of the circles. To the power of minus d, then d is the fractal dimension. The fractal is the fractal dimension. And you call this a box counting dimension, box counting one. And if you have a proper fractal structure, then this fractal dimension over here equals to the Hausdorff-Besicovitch fractal dimension. So good news is that whichever flavor of the fractal dimension you say, if you have self-similar structure, they give all the same value. The second way is doing it by considering the structures of different sizes. And if we say that the mass is proportional to the radius of the whole structure to the power of d, and then this d is called the mass dimension. Mass dimension. We have different flavors of fractal dimensions. Now, as a small exercise, we might try to calculate here the fractal dimension of this thing over here. Do you think you can do it? Yeah, you can. Arthur, do you think you can calculate this one here? Fractal dimension?
No.
Just in principle. In principle, you can do it. Okay. Well, it's actually quite easy. We can do it just almost immediately. So let us use the mass dimension, for instance, because that guy over here is made of, you can think of being made of 3 pieces. We take 3 smaller Sierpinski gaskets and put them together, and then we have 3m, 3 times mass goes by 3 times, right? Is equal to, now size became 2 times bigger. If this was unity, this is 2. This equals to And if the single one has mass m, then now it must have m times 2 to the power of d. And from here, d equals log of 3 base 2. Very easy. Now, I can give you, if you'd like to have a little bit more challenging fractal dimension calculation task. But, the task would be, you know, there is also contour dust. Contour dust. And this is like you take a segment and then divide this into 3 pieces. And you cut off the middle part. Okay. And then do the same and the same and the same. And that's why it's all quite easy, not much different. And yeah, we have here one fractal, another fractal, and then we add them together. Now size became 3 times bigger. If this is unit, if this is unity, then the whole thing is now 3. So we have mass becomes 2 times bigger. 2m equals single one has mass m, and size becomes 3 times bigger. So 3 to the power of d. And from here we obtain that d now is log 2 base 3. So now is a question: if we have a different contour dust, if our contour dust is now like that, we take a segment and divide this into 4 pieces. And now we remove only one of them. So now this is our one new piece, and this is the other new piece. And now we repeat doing the same and the same and the same. So now we divide this into 4 and remove this middle one here. And do the same here. So what is now D? Do you think you can do that? So how do you want this to be your homework, or does it look like a good homework?
Do we remove the third quarter of this?
Each time, each remaining segment, you remove one of the quarters in the middle. So you divide into 4 parts and remove one of them from the middle each time.
It's just a summatory, no? It's just a summatory, no?
Yeah, but it's a little bit tricky here to find the fractal dimension. It's not very immediate.
Okay.
Arthur, how do you feel about it? Does it look like a good homework?
Do we have some minutes to do that?
If you want, you can have right now try to think about it. Do you want to? Okay, Enrico here wants to try it. How difficult it is. What about you, Arthur? How you feel about it?
I think it's I think I have the answer, but I'm not sure.
You have already answered? You can tell me?
I got now the log base 4 of 3.
No, it's not. That's not correct.
No, okay. Then I need some.
It's more tricky. The reason is that you divide them into different pieces of different sizes. Now, one piece, one big one, this big one here is made up of two pieces of different sizes. One piece is this one here, and the other one is this one here. So previously divided into equal pieces. This is the same size as this. But now we divided them into different size pieces. So you cannot do it as easily as before because the pieces into which you divide it have different sizes. That makes it now a little more difficult.
May I ask about the first question about the triangle? Is
Yes.
it like the sum from 1 to infinity of 3 exponent I times the zero dimension, let's say the side of the initial triangle squared, divided 2 exponent 2i?
Let's go back. Okay, here. Yes. So once again, maybe you can show me. Right, yeah.
And now we compute like in some mathematical way, like from the succession. Like I don't remember how to compute successions, but
well, the thing is that actually, if we speak about fractals, we must make a difference. If we have idealized mathematical fractals, so those which we have in physics, Well, this basically works for both. For mathematical, what I did here for mathematical and real things in physics. In mathematics, you won't have like small scale cutoff. You say that all the tiniest size goes to minus like 0. The generation, you can look at the finer and finer generation, the smaller and smaller scales, and there is no limit. But in physics, you always have the smallest available scale. If not anything else, it is just the size of a molecule, right? You cannot divide it more. And then if we imagine now a mathematical object with 0, then the total mass in normal sense would be 0, because it consists of elements of 0 size. Okay, and that's why you need to have Hausdorff-Besicovitch measure. So basically, if we have a two-dimensional object in mathematics, you need to measure it in square meters, so to say, in units which go as a meter squared. If you have a linear object, then you measure this in meters. But you cannot measure the size of a linear ideal mathematical line in square meters in the same way as you cannot measure a square size of a square in meters, rather you need to have square meters. Now, in the same mathematical way, if you have a fractal object, you cannot measure neither in meters, neither in square meters, but there is something in between you need to have. That's for which you have Hausdorff-Besicovitch measure. So this Hausdorff-Besicovitch measure is a thing to measure the size of the object. And then the dimension alpha then is the number which you need to put into power. So no, not meters squared, but meters to the power of that log 3 base 2. And but now we can still use. So it's a little bit basically what we will need to do is to find such exponent as that measure is neither 0 to infinity. So if you try to measure the size of a square in meters, you obtain 0, you obtain infinity, because now how to say, if you start applying this thing here, basically you know that if you divide into smaller pieces the thing, then you are used to things that you get more precise and more precise results. Like if you start to measure the surface area of a circle, what you do is historically what you did, you started dividing into maybe squares. Okay, you know the surface area of a square, then you start filling it with squares. This is what you can easily do. And then if you go to limit very, very small squares, then this, and if you have a proper limit as a process, then this gives you the surface area, isn't it? Now, if you try to do the same thing here, it is either diverges or goes to 0, depending if you take squares or lines. If you try starting in colors with the lines and takes a limit, this goes to infinity. You need to have infinite number of so small pieces of line of total infinite length. If you take squares, it goes to 0. The total measure. So neither of them will work. What you need to have is certain like fractal exponents there. That's how Hausdorff-Besicovitch works. Now, in order to, in practice, to calculate the fractal dimensions, what you do is you use, for instance, a mass dimension. If you use mass dimension, you notice that whichever mass it is, let's say it is meters, square meters, doesn't matter. If we have certain measure for the mass, and then we add mass of this and mass of that and mass of that, your additivity may say that total mass is 3 times bigger than each of them, right? We take this as certain mass, but this has the same mass. Now I don't know if Arthur is seeing what, maybe I take here a laser pointer and show. So mass of this plus mass of this plus mass of this. Yeah, because they have the same size, obviously they must have the same mass. So mass of this plus mass of this plus mass of this gives us the whole mass, because this whole thing is made of 3 equal pieces. And that's what we wrote down. We wrote down that, as is already on next page, I guess. No, here. Yeah, here, last line here. Okay, we have here total mass of the big thing here is made of 3 smaller masses. That's why I write 3 up, okay? And then we have, on the other hand, we know that the size of the object must grow as its linear dimension to the power of d, where d is dimensionality. If you take a line, the length grows as length to the power of 1. If you take square, the size surface area of interest grows as a linear size square. If you take a ball, the volume grows as linear size cube. So the power gives us the dimension. Now here we have object, the same fractal object, but 2 times bigger in linear size. So we take 2 to the power of d, and so if if the size of the small thing was m, now it must be m times 2 to the power of d. And then this equality here is equality which gives us d. Is it okay, Enrico? I don't know if I answered the question, but just explain all over again.
I can understand how the measure unity of the area is not, it's like in between 1 and 2.
Yeah.
And basically that's like basically I didn't understand really.
Yeah, this is actually, yeah. This has to do with this Hausdorff measure. Is a measure to which you need to use if you want to compare 2 fractal objects of the same dimensionality. So if you want to measure 2 objects which are planar, then you compare by surface area, which is in square meters. If you compare 2 wires, you compare the total length. Or length of them, meters to the first power. Now, if you have 2 fractal objects and you want to compare the sizes of them, and you know that the fractal dimension is the same, you cannot compare sizes of 2 things when the dimension is different. You cannot compare the size of a line and size of a square. Well, you can say that square is by definition always bigger. If you have dimension bigger, then the object is bigger, in a sense. And so the only meaningful thing to measure is the 2 objects which have the same fractal dimension. And then to that end, you have a so-called Hausdorff-Besicovitch measure. Hausdorff-Besicovitch measure is with which you can measure the size and compare the size of 2 fractal objects which have the same fractal dimension, the Hausdorff-Besicovitch dimension. And you just make it the same way, the definition, as you make the surface area. So you start dividing object into smaller pieces, smaller squares, and sum up the linear size of the square to a certain power. And if you go to the limit where the size of the squares goes to 0, then if your result is diverging, then your dimensionality what you used is too small. Like you take a square surface, try to measure square in square meters, but you sum up sizes of all the small squares to the first power. You have so many squares that the result will diverge. It goes to infinity. So you use too small number. On the other hand, if it goes to 0 at the limit, then the other way around, you use too big number. So if you try to measure the size of a line as a meter squared, you divide into small pieces and take this length of the piece to square. The number grows slower. It goes up slower than the length squared goes smaller. So the result will go to 0. It's also normal. So you need to take the correct power in order to have something which is neither 0 nor infinity. and that's the correct dimension. All Hausdorff is gauge dimension.
But then when like we compute the result, the final result, like it will be the same in the, let's say, mathematical like summatory, right?
Yeah.
Okay.
Yeah, but here actually usually the task is not so much to compute the Hausdorff gauge measure, but rather to calculate the fractal dimension. This is what usually is a scaling exponent is usually more important. And we are also doing here calculating the fractal dimension instead. And in order to calculate fractal dimension, usual ways are either so-called box counting method, in which case you divide the object into small pieces of a given size, and then let the size go to 0 and count how many boxes you need. And then this is what you have, box counting dimension. Number of boxes goes to the size to minus d, then d is box counting dimension. Alternatively, you can use the mass dimension, in which you say that mass grows as a size to the power of d, and that's what we used here to calculate the fractal dimensions of contour dust and of Sierpinski gasket. And with all that said, so how you feel about this the last task? So you think you can do it?
Still not sure I understand the n3 to the power of d.
Ah, okay. Okay. Then this is the same thing what we did for Sierpinski gasket, but now for contour dust. So what we have here, I didn't finish dividing the drawing. So okay, we divide this. Oh, sorry, now it became too much. I did it too much. Okay, here we delete middle, here we delete middle, and then again middle, again middle, again middle, and again middle, and now I think I cannot do it no longer. So we have like a point, set of points, but there are somewhere the points are like more densely populated, and there are bigger gaps in between. That's what you have here now, and now we calculate, apply the mass dimension again. We say that okay, this piece here has the same size as this piece here. So let the mass of this piece here be m. Then the total set what we have here has two such pieces, so total mass is 2m. Okay. Now, if this has unit length, then this guy here has length 3, right? One piece is the gap of the same size, another piece. So total length 3. And now, if we have that scaling law that mass is proportional to the size to the power of d, then if this piece here had mass m, this thing here must have mass bigger by a factor of 3 to the power of d, because we know that mass must grow to the size to the power of d. It's 3 times bigger, so mass must be bigger by a factor of 3 to the power of d. And then we write this down this relationship. Two pieces gives us m3d. And then if you express here, it's just one step away, a simple step to update it, right? Take log base 3 from left hand side and right hand side. This gives d, and this gives log 2 base 3. All right, is it clear now? We did exactly the same with the Sierpinski gasket. You want me to repeat again? Here we have 3 pieces. This has size 1. This has size 2. Okay, let us see. We have 3 pieces, 1, 2, 3. Total mass 3m. Now size is 2 times bigger, so it goes to 2 to the power of d. Okay, and we express and there you are. All right. Now, how you feel about this last task? Arthur, maybe you have managed to find answer over there. I mean, this asymmetric contour dust. Do you want this to be a homework? No, why not? If you don't manage to do it, we can do it later on. Do it, so don't worry. Why I'm saying this, it is not. It depends on you. You might. The solution is not difficult actually. The solution is quite not that difficult if you use that method which what I did before. On the other hand, you might try doing it also using box counting method, and then it becomes a little bit tricky, I guess. But yeah, you might have something like. Well, we might try starting working out it. Let us see. I can give you also another approach to this. So actually, that is easy way to find it, but just for fun, I can give you another. Just like let us start doing it with box counting method. So if we try to cover this with a big box, now which color I use? Let us say red. So I'll cover this with big box of size. Now let's just be size 1. Okay. Size 1 big box. Okay. Now let us make size 1.5. Oh no, let us say make size yeah, maybe two times smaller. 2 times smaller. Now we have a box this and boxes. We still need to have 2 boxes to cover. Now, okay, here let's make table. Length of the box and number of boxes needed to cover. If length is 1, number of boxes is 1. If length is 1/2, then number is 2. But if length is 1/4, then what? And then we have here 1 box. Here we have another box, and here we have now this length is also 1/4, right? No, did I now do it correctly? No. Okay, this way. This is 1 box, this is another box, and this is another box. Is that correct? I think so, yes. So now we have 3. And now let us take make it even 2 times smaller. Now what happens? Now here we have 1, 2, 3, 4, 5. Okay. Okay. This is bigger, like that. Now we have 1/8, and we have 5 boxes. What do you think? What will be the next number? Any guess? You want me to calculate? Can you make your guess now? Raina has some idea. So what is your guess? What is next? 8. Yeah, 8. And now what is the next one?
It's not Fibonacci.
Yeah, it is Fibonacci. It is.
13,
yeah, 13 is next. Yeah.
34.
Yeah. Now, yeah. With that, you can already calculate, I guess, isn't it? After you know Fibonacci, right? Yeah. So we have Fibonacci sequence here coming up. So now you don't have actually a strict scaling because now actually here we obtained this exponent straight from the first step. Only one iteration was needed, but here we need to have many iterations. And actually, the answer is that actually this d, what we obtain, this is at the limit. N goes to the infinity, or if we speak about mass, then mass goes to infinity, or something like that. So at the limit of asymptotic limit, actually, it's exponent asymptotic limit. So Fibonacci, you don't have here actually for the small n's, it is not strict power law. But if you take big n's, it becomes asymptotically closer and closer to a power law. Okay. With that, I think you'll be able to do it. What do you think? You can make some research. Yeah. Ja, mis see?
3/4 on see kogu aeg, see 3/4 läheb väiksem.
Aga siin ei ole.
Ei ole.
Siin ei ole. So shall we keep this first home task? So my suggestion is actually to solve it now in two ways. Find fractal dimension based on this sequence of numbers here. Like you make research how behave Fibonacci number at big n value, and then the next thing is to try obtaining the same result in the same way as we wiped out, or more or less in the same way as we wiped out this dimension here, this log 2/3. Yes.
From the Fibonacci series, how do you use them? Do we have to use some ratio? Or...
Actually, I am also free to explain you a little bit about Fibonacci, which is also kind of educational. It's not strictly speaking turbulence, maybe, but it is educational nevertheless. A little bit more math. How do you want me, or do you rather want me to continue with turbulence mixing? Do you want me to explain about expression for Fibonacci numbers?
Like where the reference number comes from and so on?
The expression, what you need here, basically. You want?
Yes.
Everyone out there, you also want? Okay. So Fibonacci numbers. So Fibonacci numbers are defined as xn plus 1 equals to xn plus xn minus 1. And x0 equals to 0, x1 equals to 1. Okay. Now this is very similar to linear differential equations of the second order. Can you see? Let me write. Let me rewrite this. So we have x
because the xn is equal to the difference of the two values.
Yeah.
Like
So
before
x
and after.
xn plus 1 minus xn equals xn minus 1. So here this is like a difference, and this here is the function itself. So basically, how you solve equations, differential equations with constant multipliers. It is you write down characteristic equation, right? And you find the root of this. So in the same way, actually here, you can look for solutions in the same way. So if we had characteristic equation for equation something like x to the second power plus a x to the first power plus bx equal to 0, then you write down equation lambda squared plus a lambda plus b, because you look for solution in the form of x equals to e to the power of lambda t. Now, what does it mean? It grows linearly with t, exponentially with t. Now here, where is our t? T is actually n, isn't it? We relate here derivative, but derivative like approximate derivative is is this. So x derivative goes to basically to xn minus xn minus 1. So here we have, if we have function, let us say x of t. So we have something like that. And for this guy over here, you take tangent. You take tangent to the curve. Okay. Now, in the case of difference, you take, instead of tangent, you take 2 points, the 2 points on the curve, which is slightly different from the tangent, right? But still very approximate. So instead of tangent, which is delta d x over dt, here you use delta x over delta t, where delta t is 1. So instead of x derivative, it goes to delta x over delta t, where delta t is 1. Okay. So this means that you should now look for solutions also in a similar form, that xn is a certain prefactor, which you don't write down at the moment, just the same way as we look here exponential, we take certain a to the power of n. The same version, right? You can see it, I hope. So now each time you increase n by 1, the result goes bigger by factor of a. Here, in the case of differential equation, each time t increased by 1, you multiply the result by to the power e to the power of t. Okay, and this is like a motivation why we do it and how it comes. So we look in this form and put in here. And then we have a to the power n plus 1 equals a to the power of n plus a to the power of n minus 1. And from here, a square minus a minus 1 equal to 0. And a equals 1/2 plus minus square root of 1 over 4 plus 1 5/4. Equals 1 plus minus square root of 5 over 2. We have two roots now. What should I do? A1, A2. So in the case of differential equations, your generic solution is superposition of those two solutions. In the same way here, actually, you have many solutions to this differential equation, and you just can have, again, the same superposition. So superposition of two solutions of this differential equation, recursive expression here is a superposition of those solutions what we have found. And now we have one solution is xn is a to is the first solution here, a1 to the power of n, and also we can have xn equals to a2 to the power of n. But we can also have linear combinations of those. So we can have xn equals to a1 certain first prefactor a capital A1 to the power of n plus another factor b and a2 to the power of n, and divided by no, not divided by, yeah. And now the question is, what is a capital, what is b capital? And we need, of course, to satisfy those two initial conditions. The guys over here. So we need to, if we put in now n capital equals to 1 and let us make 0 and 1. So we must obtain 0 if we must put in n equal to 0. So 0 equals a and a1 to the power of 0 plus b a2 to the power of 0 equals to a plus b. So a equals minus b. And now we can use this and say that 1 equals a and A1 to the power of 1 minus A2 to the power of 1. So that A capital is 1 divided by A1 minus A2. But what was A1, what was A2? We have two solutions here. We take the difference of them. So the difference becomes square root of 5, isn't it? And here we are. We have now everything available. We can write somewhere solution where we have still some space. So xn equals 1 over square root of 5 and 2. So 1, let us write 2 square root of 5 and 1 plus 1 plus square root of 5 to the power of n minus 1 minus square root of 5 to the power of n. And here. Okay. And actually, the lesson is that if you have such kind of difference equation of arbitrary order, actually it comes down again to characteristic equation, algebraic characteristic equation. So we can also in the same way as long as the vectors are constant. So such kind of difference or recursive expressions can be solved as long as the factors are constant, and as long as they are linear. So what we had was at hand was linear difference equation, because xn was everywhere to the first power. X. It was linear, so we were able to solve in the same way as you are able to solve linear differential equations with constant vectors, with characteristic equations. All right. Now, with that at hand, it should be already very easy. You just what you need to do is analyze it asymptotically as n goes to 3. Now, let us do one time fast, and we have still only 20 minutes left. So, actually, that was a reason why I started talking about fractal dimension. So, if we go back now to the first this figure here, actually it appears that this thing here can be also characterized in terms of fractal dimension. What we have, what you'll be having here, and this is called Lyapunov dimension. So this guy, this thing here is described by Lyapunov dimension. And let us try to obtain expression for that. Now, let us try doing it using mass dimension. So suppose we have a certain piece over there, the trace around the surface, which occupies a certain area, like that. Oh, well, we can make it quadratic at the beginning. It was quadratic at the beginning, and then it went into this shape. And then it's even further compressed, even longer and even narrower. And now length here is described by the largest Lyapunov exponent, E lambda 1 times t. The cross dimension is described by second largest, E lambda 2t. And now what we would like to do is let us try to calculate this, like maybe mass of this thing here. We see that actually it becomes what was stretched like linear, it becomes a linear structure becomes longer and longer and longer. It's like a kind of one-dimensional structure. So so if we cover voice boxes which are if for instance if we try to start applying the box counting method, then the number of boxes actually is the length divided by the radius. So the total length is L, and N here would be because it becomes narrow and narrow and narrow. So as long as the circle size is not smaller than the width of the structure, so it behaves like a one-dimensional structure. So n number of boxes in order to cover it longitudinally just grows as length L, which corresponds, in order to take care of covering the mass grows in that longitudinal direction. You need to have this contributes to the dimension by 1. So L to the power of 1. On the other hand, we have still what question: what happens in the perpendicular direction? And so let us say that this guy over here has total mass of m. Now let us calculate the mass per perpendicular direction. So if length grows as e to the power of lambda 1t, then the linear mass density, meaning mass per unit length of this linear structure over here. So let us say rho linear is inversely proportional to L, and this is proportional to e to the power of minus lambda 1t. And now, as this box evolves, the mass in the perpendicular direction grows, behaves in the same way. So as this guy over here. But now let us see how it scales with the size in perpendicular direction. So the size itself is, let us denote this like maybe delta. So delta, we know that delta scales as e to the power of lambda 2. And sorry, not rho but delta. Thickness goes down as e to the power of lambda 2t. And now if we try to express this linear density in terms of delta, then what happens is that rho L to the power of lambda 2 is proportional to e minus lambda 1 lambda 2 t equals to, is proportional to thickness delta to the power of minus lambda 1, isn't it? With these scaling laws what we have. so that linear density rho linear is proportional to delta minus lambda 1 divided by lambda 2. And so we can interpret now this the mass in perpendicular direction has a scaling law with the thickness, and this if we speak about a fractal dimension of this whole structure, so it has a linear in one direction, contributing to dimension to 1 in that direction, but in perpendicular direction it behaves like a fractal structure with this exponent over here. So that we say that the total fractal dimension, which was what we call Lyapunov dimension, is going to be that unity which comes from the fact that it's one dimension here, plus this exponent for what comes from over there. So now lambda, we assumed here that maybe I have made some sign mistake as well, but okay, let us see. This guy over here, I think I made certain sign mistake. We because actually we assume that lambda 1 is positive, lambda 2 is negative. So delta, if lambda 2 is negative, we need to have put here modulus of lambda 2. Modulus of lambda 2, and we keep here also modulus of lambda 2 everywhere. We assume that lambda 1 is 2, and then we have Lyapunov exponent coming out as lambda 1 divided by modulus of lambda 2. I'm afraid it was a little bit messy. I myself felt that the explanation did not go very smoothly. Maybe I just repeated once again what was happening. So we want to describe this thing here, what we have on this figure, with a fractal dimension. We see that we have linear structures forming over there. We have here kind of a linear structure. So if we start covering these boxes, and then the number of boxes to cover it in that direction, just this linear function of the is inversely proportional to the size of the box. So here this works out as a one-dimensional structure. But the mass scales with the width. And then, if we want to now apply like the combined way with the mass dimension, then we say that, okay, if linear density here of this thing here is a power law of the thickness, then that the thickness goes to the fractal dimension describing the structure in the perpendicular direction to this stripe. So this is a stripe in perpendicular direction. This is described with that exponent, which relates the mass per unit length of this structure here, how it scales with the thickness. And all we do is express the mass in terms of thickness. So thickness delta goes like E lambda 2 I think I have still here a little issue with the exponents. As the thickness, it goes down. Here we have minus. Yeah, we must have minus. Thickness goes down as because lambda 2 is negative. Thickness goes to E lambda 2 to T, but if I want to use modulus, I put minus sign before. Now, on the other hand, the length grows as e to the power 1 divided by the density of this linear structure. Because the total mass is conserved, it goes down as 1 divided by length. And length is e to the power of lambda 1, so that the whole thing becomes e to the power of minus lambda 1 t. And then rho density to the power of lambda 2 now density goes because we have expression here for density over here. So if we take this to the power of lambda 2, we have minus lambda 1 and lambda 2 modulus. And then this thing is a thing over here. On the one hand, and on the other hand, if we compare this with the expression for the thickness delta, which is over here, we see that we need to take this to the power of lambda 2. Yeah, just so the only thing is everything is correct except I need to have here plus. So density, the mass is proportional to the size to the power of lambda 1 divided by lambda 2. So that guy over here is interpreted now as a fractal dimension describing the thing in a perpendicular direction. Well, more or less clear what's going on in the material.
Yeah, like the idea, the principle, yes, but like I could never recall this idea from the whiteboard. Like, and also my notes are even worse than the whiteboard. Like,
okay, and so anyway, people use Lyapunov the dimension to describe the kind of fractal picture what you have here. Kind of fractal picture. So which means what does it mean? It means that here that if we take if you were to take one stripe over here, like thicker stripes and narrower stripes, which are shorter. If you compare those different stripes over here, so similarity, mass of this and mass of this are related to each other as a linear size to the power of d. So length grows the total mass is contributed by the length and by the mass per unit length. So mass of this related to the mass of that is on the one hand, we assume this to be linear dimension to the power of d, which is the thing over here. But on the other hand, this comes down as a length multiplied by the mass per length. And that's exactly what we did in our calculations. In our calculations, we found a mass per length rho, and on the other hand, we said that the length contributes to the exponent by 1, and mass per unit length contributes by that guy over there. Arthur, how you feel about it?
So, okay, until the last step where you define a dimension as 1 plus lambda 1 over 2, is it just adding the two together, or is there a reason behind this?
Yeah, so the reason you are doing this is that, once again, we want to have, let me try perhaps recap still a third time. So we have one structure over here, this stripe over here. Then we have another one, which is over here. So if this length is, let us say, L1, and this one here is L2, then we want to have mass over here, mass to be M1 to be equal to M2 multiplied by L1 divided by L2 to the power of d. That's what we expect from fractal dimension. Okay. Now, on the other hand, that M1 is equal to mass per length multiplied by length. So the ratio of the masses comes from the fact that the diameters are different. So L1 divided by L2. This gives us how many times the mass here is bigger because the second structure is longer. On the other hand, mass is also a proportion to linear density, length multiplied by density. So ρ1 divided by ρ2. Okay, now ρ1 divided by ρ2, we found out that this over here is proportional, is equal to L1 divided by L2 to the power of lambda 1 divided by lambda 2. Was equal to so 1 divided by ρ2 is L1 divided by L2 to the power of lambda 1 divided by lambda 2 modulus. Okay, so all together, this thing over here now is equal to lambda L1 divided by L2 to the power of 1 plus lambda 1 divided by lambda 2 modulus. And then we say that this one here is D because that's the power law expected. Okay?
That makes it clear. Yeah, thanks.
Oh, sorry, it became drawing became a little bit messy, but as long as you understood, I think it's it might be would have been explained definitely better, but feel free to ask questions if you still feel insecure here or there.
Is there some material on which we can study like as a book or like the lecture is fine, but like without like lecture notes or some like you know like
yeah. You already asked this, I think, last time, and the answer is still no, because in order to have that, okay, so people, I can give you papers where people calculate that Lyapunov exponent for turbulent fluid fields. But then if you go through the references, how they calculate, this comes down to a fairly fixed theoretical material regarding dynamical system, Kaplan-Yorka dimensions, and like strange attractors, fractal dimensions of them. And so these things become, if you want to go through these textbooks, I really don't recommend because it's too much reading. It's way more reading than we get six grade points. So that's why I am not giving you those references.
But how can we prepare the exam if like?
Okay. So as for exam, requirements for exam are basically homeworks which you we can guide through. So if you rather here trouble, you had a consultation. I can also, if you have trouble with some problems, we can make an appointment for his consultation. Of course, it would be better if you can do it that way by yourself, but if not, then we'll find time slot for you. And if you are away internet, you can find also a time slot over Skype or so. Then again, if we, in addition to that, I want you to have that home project more or less completed, and we may have a short discussion, like I asked you, few concepts like theoretical concept, but definitely not details how to derive this or that. Just so that you know the most important basic concepts, and then I can write you more or less the questions what you will be having before the exam. Like maybe explain quality for this topic here, for instance, explain qualitatively why a particle in the compressible fluid start gathering into patches. Meaning that I expect from you to say that, okay, because averaging over trajectories is different from averaging over space. Averaging over trajectories of particles of divergence gives you something which is negative, which means that they start gathering something like that, for instance. Or, well, yeah, I can ask you what describes that Lyapunov exponent in the case of compressible fluid, and then you can just state that describes how the mass of structures over there scales with the size, and just if it would be particularly good if you can give me also the formula for that. So don't expect me to ask you too difficult questions on the examination. So I'm not asking you anything more than we are doing here, and rather I don't require all the mathematical derivations. Of course, it would be better if you more or less understand them as a mathematical derivation, because just to take things on your trust is not never too good. But yeah. All right. Now, before I let you go, time is more or less already up. But before I go, let us see what we have. So we conclude that fractal dimension. Let us have a look now on the fractal dimension. So what we here actually assumes that is lambda 2 is negative, lambda 1 is positive, actually, because there is plus sign over there, and you have something like structures which are one-dimensional and a little more, like scale in one direction and somewhat also mass distribution in the perpendicular direction, like a Cantor dust like thing. And so you would expect that in the perpendicular direction is something like Cantor dust, what we did before. In that direction it's linear, in perpendicular direction it is like Cantor dust. And yeah, it looks exactly like you see here. It looks exactly like you see in this figure over there. But then let us still go back and look the expression of what we had for lambda 1 and lambda 2 over here. And pay attention that if the compressibility C becomes bigger than 1, then this thing here becomes negative. So and now this, let us add one more page over there. Or maybe it's the end of the thing. So NB if compressibility is bigger than 1/2, then lambda 1 is negative, so which means that distance between particles starts decreasing. You remember we made a log normal graph. So here we would also have interparticle distance. For interparticle distance is log normal graph. So here is logarithm of length, and here is vertical is PDF probability, and horizontal is logarithm of length. Vertical is probability, and horizontal is logarithm of length. So if we had incompressible flow, then we started from Dirac delta function here, and then this goes to something like that over here. So you have average logarithm growing, and it becomes widening. Now, if we have compressible flow, and if compressibility is bigger than 1/2, then actually this guy here goes actually that way. So the interparticle distance starts decreasing, and this is called strong compressibility. If lambda1 is smaller than 0, then strong compressibility. So everything will gather into single batches. All the particles go together. If we look back here, so here is basically compressibility is around 1/2. So it's like limit case between 1 and 2. And particles are not yet into, don't go exactly into single cluster, but you have a lot of distribution over here. These are a little bit more complicated also because these are like a lot of small particles. They just cannot everything clamp into single point because they have physical size. But if you had a very small size and particle could go if they close to each other, if your compressibility is smaller than 0, bigger than 1/2, then they all the traces on the surface would gather into single batch. And real life on the water surface basically between the two. On the other hand, there are also cases when compressibility is bigger than 1/2, and this is called overdamped motion of Brownian particles. We can speak a little bit about that next time. So compressibility equals to 1 is overdamped motion of Brownian particles. Okay. And then the next plan is that the next time we'll speak a little bit about that, and then we speak about compressible turbulent flows together with Richardson's law, like interparticle distance between incompressible flows in the case of turbulent flows. I'll give you, and then I go to Kolmogorov turbulence after that. So we are finishing up the tracer part and going to the fluid dynamics part. I'm not sure, we might not reach the Kolmogorov turbulence next time, but maybe after next time. So next time I give you like results for Kolmogorov turbulence in order to be able to derive the Richardson law for tracer particles. But we derive a Kolmogorov law and later. All right. So then, until next time. And yeah, don't hesitate to ask me to have like make a consultation appointment if you need. So one possibility is those guys who are here, you can stay like here after selection time. You can make here over internet. You can also at any time when I'm more or less free. So. Arthur, do you have any questions?
No, I don't think so at the moment. So if I have them this week, I will send an email.
Okay, all right. And you have got your homework this time already? No.
Process.
Right.
Until next time. Particles in the box. Like this.